more interesting is our speaker, who is Stan Williams from Texas A&M University, my former mentor. So please give a warm welcome to Stan.
So thank you very much. I really appreciate your interest. This title of this presentation is completely meaningless. When I was asked to send a title and abstract, I had no idea what I was going to talk about. And in fact, I just figured out what I was going to talk about a week ago. So it's going to be a little different. Also, Rainer was very, very insistent that I not do my usual thing, and that is go crazy and show way too many view graphs and way too much detail. So so last night I actually cut out half the view graphs in my presentation. So what I'm going to try to do is, let's see, first of all, acknowledge that there's been a few very important people who have worked with me on this particular aspect, this particular issue that I'm working on, and Leon Chu, of course, with his theories, and then I've had very, very talented experimental assistance from some some really excellent folks. So here's the deal. Rainer wanted me to have a high-level objective. So what I'm going to do is I want to try to get across just two ideas, and only two. And if I succeed in doing that, I think I will have done what I really wanted to do. It turns out that there's this area called nonlinear dynamics. This is the area that Leon Chua really has developed over the past 50 years. And in particular, I'll call it the dynamics of non-monotonic systems. In other words, systems where you have an excitation and the response has a peak and then starts decreasing after some time. So an example of this is negative differential resistance, but it's not the only issue that exists. But it turns out that this non-monotonic response is the source of amplification in brains. Now, most of us don't really think about the fact that neurons are amplifiers, but they are. There's no three-terminal devices. Brains are capable of amplification if the neurons are essentially biased at a particular point in their characteristic. So without amplification, there's no computation. But my goal is no transistors. So I'm trying to build systems without transistors that have all of the amplification that's required in order to do neuromorphic computing. The other issue is there's an entire field called stochastic thermodynamics, which has grown up, and surprisingly, it's been fairly quiet. But in particular, the issue there is that fluctuations, I mean, you heard about noise, right? I'll call noise fluctuations. That fluctuations essentially drive entropy production minimization in a dynamical system. And this entropy production minimization gives you power efficiency. It essentially makes the system more efficient in terms of power. And so this is why, in my view, the brain is willing to sacrifice some issues in terms of having a noisy environment, because the power efficiency that you gain from the noise is huge. In fact, if it weren't for this entropy production minimization power efficiency, our brains could not work the way they do. Our heads would explode. All right? So I'm done. I got my 2 points across, but I guess we'll just try a few other things. So here's an experiment. Now, those of you who know me know that what I try to do is I try to go into the laboratory and confront theoretical models with experimental measurement and make sure that we understand what's going on. So here's a specific experiment that was done by Tim Brown, mostly, and some others that work with me. And so what did we learn by doing these particular experiments? Well, if you have a system, okay? In this particular case, we're going to look at current versus voltage. So if you drive a current into the system, this is current controlled, and look at how the voltage goes, you see that the VI curve goes up, and then it rounds off, and then actually it decreases rather abruptly. When this happens, when this decrease in the IV characteristic happens, two other things occur simultaneously. Okay? One of them is that the system starts oscillating. And in fact, these are effectively action potentials. So you've got a system that when biased at a particular current, in this case, you will get a set of oscillations, and it turns out that Leon Chua's theory of nonlinear dynamics allows you to calculate the intensity and the frequency of these oscillations very, very well. So we actually understand this. However, there's something else that happens almost simultaneously, maybe not quite, and that is, I pointed out that there is this sharp decrease in the device voltage. And when that occurs, what we see is that we can measure the temperature with very high spatial resolution in our devices, and what we see is that there are these channels, high temperature channels, that form in the device. So all of a sudden, you have this concentration of current density, and it is accompanied by a sharp decrease in the voltage of the system. Okay? Now, here's the interesting thing. These are two very different observations. They each have their own theory. So this observation here is explained by the theory of local activity. This theory here, or this experimental result here, is explained by stochastic thermodynamics. And here's the crazy thing. There are two completely different things going on in neurons and in these neuromorphic devices that we're building. Can you? All right. There are two completely different theories that explain these two observations, these phenomena. These two theories have been around for 60 years. And that has yielded what I'll just call 60 years of confusion and ambiguity, and an awful lot of animosity between the two camps. It's, you don't know what you're doing. I've done my theory, and my theory works, and therefore it's right and you're wrong. Neither side tried to understand what the other was doing. And so there's literally been a 60-year-long fight between these two camps about what's going on in these systems, and yet they're both right. Or maybe they're both wrong, depending upon how you want to look at it. So what I'm going to try to do here is clean this up a little bit, is sort of go over some of this 60-year history and show what the deal is, and why neither nonlinear dynamics nor stochastic thermodynamics is a perfect explanation of these systems. You need them both, and you need to be able to combine them together. All right? So here's another paper. This may be the most important paper I've ever written. It's got like, I don't know, 20 citations. This is the result of 17 years worth of effort on my part, plus 2 years of COVID isolation where we sat down and wrote the paper. But what we did here is went through Leon Chua's theory of nonlinear dynamics, which is completely mathematical, and we translated it into a form that hopefully can be understood by material scientists and device physicists. So we had to essentially take a theory which had no material, had no dimensions, and recast that theory in terms of something real, something that you could measure in the laboratory. And having done that, the level of understanding that I've been able to gain is tremendous. Now, the problem is that this paper itself is not exactly a simple thing to read, and I apologize for that. It's fairly dense itself, but believe me, it's a lot easier to get through this than the 17 years that I spent attempting to understand the theory in the first place. So the issue is we want to be able to transform to measurable material properties. This was not something that was anywhere in Leon Chua's theories. His theories were just, everything was axiomatic, everything was toy models. So what we did is we went through and we essentially figured out, wow, if you have electronic or thermal responses to a stimulus, either voltage or temperature, either one can provide the nonlinear effects that are required to create this amplification that I'm going to talk about. So it's not just voltage, it's voltage and temperature. They're both important state variables. And at least one of these parameters, at least one of these properties, needs to have a large derivative in order for you to be able to have a material that has this property of amplification. So what is the source of the amplification? So it's the ability of a material, of a device or a material, to amplify small pulses or fluctuations. And the way it does that, in terms of being a memristor, is that the memristor has to have a phase shift between its current and voltage. And it turns out that that phase shift needs to be greater than pi over 2. And once you've essentially gone above that phase shift, now all of a sudden you've got an amplifier. Now, this is not something that people have really thought very much about. All right, this is, people have talked about memristors and it's not really a fourth element or whatever else. But because these things actually have phase shifts, and even larger phase shifts than either inductors or capacitors, you can bias a memristor device into a realm where it acts as literally a perfect amplifier. Okay. Now, the problem is to convince anyone that this is real. And this took an absolute tour de force measurement to be able to do this. We literally had to build our own experimental apparatus. The stuff that you buy from commercial companies is useless junk. It's expensive. You've got no idea what's inside of it. The companies won't tell you. You're essentially taking a black box and you're attempting to make a measurement on another black box. And so you either have to calibrate this commercial piece of equipment like crazy, or throw it away because, in fact, much of what's inside of those black boxes is not useful. So we literally had to go and build our own power supplies, for instance, because the existing DC power supplies have too much capacitance. So we had to build a very low capacitance power supply. And when we did that, we were able to take one of these devices. And so here you see this IV characteristic again. And so we stop before we get to the jump downwards. But you see that this is labeled as passive and EOC for edge of chaos. Now, edge of chaos is jargon. I wish that didn't exist. I'm stuck with it. We're all stuck with it. It seems too magical. Edge of chaos just simply means that you've got something that is both locally active, in other words, it has this capability to amplify a small signal, and it's controllable. So that's the issue here. So what we did was, if you're on this passive part of the curve, if you're ramping the bias voltage or the bias current up, and you stop at some place in time, and then you just look with a capacitor at what's happening across the device, you see these oscillations. And the current and the voltage are right on top of each other. And you would expect that. It's just a resistor after all. It's a nonlinear resistor, but nothing really crazy. However, when you get up to the maximum in this voltage versus current plot, all of a sudden what you see is that there is a phase shift of pi over 2 between the current and the voltage, and the current starts oscillating. I mean, the voltage. I'm sorry. It's the voltage. The voltage. It starts to amplify fluctuations in the voltage. Now, push this a little bit further. Push it out into this region of what we call edge of chaos. And now all of a sudden, you have a phase shift between voltage and current, which is pi. All right? That's a perfect amplifier. And it's just a piece of material with contacts on it. Okay? This is what goes on in the types of devices that we talk about when we're talking about neuromorphic computing. It's what happens in the neurons in your brain. It's just that people haven't had the experimental apparatus to measure these things appropriately. All right, and so you can make phase plots of these things and show that you've got regions of passivity, boundaries between passivity, for instance, and edge of chaos, and then you can go into the edge of chaos regime where you've got 0 phase shift, pi over 2, and pi phase shift, and then you've got this whole region down here which we call locally active but not EOC, and this is where things just jump around uncontrollably. This is like a first-order phase transition, so it happens, but you can't do anything with it. Now, let's look at the issue of the stochastic thermodynamics. This is a really cool paper. Notice the date, 1935. This name here, Schottky. In 1935, at the Siemens laboratory, this group of people took a copper oxide disk, which was one of the major semiconductors of that era, because semiconductors were still under development, and they put nickel electrodes on both sides, measured the IV curve, and instead of seeing an IV curve that sort of goes like this, they saw this sharp drop, which I've shown you before. This is what we observe. But this was observed in 1936. And what's absolutely cool about this is that they had a very good theory for it. They were talking about on the technical control of thermal breakdown. They were aware that this was not a result of thermal breakdown. This was a reversible transition caused by what I'll show you is entropy production minimization. This whole area of research just disappeared for nearly 30 years and was picked up again by Brian Ridley. And what he wanted to do, his goal was to come up with a general theory, a general construct for being able to understand what would happen if you got a material or a device with a negative differential resistance in it. In this particular case, we'll call this an S type of system. You have electric field down here and current density up here. And essentially what he was literally able to show graphically is that if you bias this system here at J naught, at this particular current density, this system would become unstable and it would start to fluctuate. And those fluctuations would essentially be going up and down in terms of this field. And if the fluctuations were able to actually push this thing over the top of this effective barrier here, what you would get is a sudden stepwise decrease in the voltage of the system, which you've seen a couple of times. You've seen it from Schottky, you've seen it from our stuff. So what he understood and what he realized is the driving force for this was entropy production minimization. In other words, you've got a dynamical system. It is exploring its phase space, and it wants to minimize entropy production. And I'm not going to get into that right now, but it took me weeks to figure out why it was entropy production. But it turns out if you try anything else, that doesn't work. It's only entropy production minimization that actually is reasonable. And so you get this sudden and sharp drop in the voltage of the system. And that sudden and sharp drop in the voltage of the system also is a sudden and sharp drop in the power dissipation, which essentially is the optimization of the power dissipation in the system. Now, if we look at the same type of drawing and use the approach from nonlinear dynamics, instead of having a system jump from here down to these lower values of voltage, what you would have is the system is constrained at a particular voltage, and it can either jump up or it can either jump down or jump up. And it can't do both at the same time. In this particular case, you get both at the same time. You get two different current densities flowing through material. In this case, you either jump up or down, and it depends upon the initial conditions that you put into your system. Here's the problem. Look at this jump up. All of a sudden, if this system decides to jump up, the amount of power dissipation goes up remarkably. And so if this were part of your brain architecture, you would just have smoke coming out of your ears. All right? So now why it was that these two different groups of very, very smart people over a period of 60 years never got together and actually figured this out, I really don't know. But at least they left something for me to do. Now here is this same thing shown in a little bit different way. This plot here is a plot using experimental parameters, if you will, but this is from the local activity theory. So you see that the system goes up, there's a maximum and a negative differential resistance. But then what happens in this system is if it jumps to much higher current, dramatically increasing the power dissipation. Not good. However, when in real systems, although the people who did the theory actually didn't really understand this, in real systems what happens is you come up here, you get to this point, and the voltage drops, the power drops, the current density essentially goes into a thin channel inside of the material. And so this is a, what I'll call this is, it's a necessary price that you pay to have the power in your brain optimized. Without the noise, you wouldn't be able to essentially minimize the entropy production in the system. So it's a very different way of thinking about things, right? Okay, so we actually have also done a very simple study of this power optimization, if you will, or this creation of a channel. Another little paper here, and this particular work just kind of blew me away. I had this graduate student come up to me, and she said, "Well, I'm going to do a COMSOL simulation of this effect that we've just discussed." And I go, "Ha ha ha ha." That'll never work. Well, it did. And that's why I learned a long time ago to never tell a student not to do something. So what she did was she essentially created a model which had material parameters like of vanadium dioxide, and she essentially flowed current through the system, and you could see that at these two currents, 2.4 milliamps and 2.5 milliamps, the system was relatively uniform. And then what she did is she made a very small temperature excursion here, here, and then here. What happened was nothing, and then all of a sudden, boom, the system collapsed. The current went into this narrow channel. So what this shows is that even at the level of COMSOL, a uniform current density in a system which is at negative differential resistance is incredibly unstable. It wants to fall apart. And in doing so, what it does is it figures out a way of minimizing the total power dissipation in the system. So there's essentially now two things that are going on. There is the usual nonlinear dynamical theory for a memristor, which has a conduction equation and a dynamical equation. But then there's another equation here, which represents the entropy. And you say, oh, well, this is trivial. This is, I'm just dividing this equation by T everywhere, and it's the same equation. Well, it's not, because we've got to minimize this. And it turns out to be awfully hard to do. At least I haven't been able to do it yet, so maybe one of you folks will figure it out. And so what I'll do is I'll end here and see if there's any questions.
Thank you very much, Stan. And so we can take some questions here.
So Rainer, did I get 2 points across? Okay.
Very interesting work, Stan. Thank you. So you showed us vanadium oxide devices, can spike, beautiful, neuromorphic, right? But how does it compare with CMOS if you look at density, energy efficiency, speed and scaling, and also the...
Well, everything that we've ever compared is orders of magnitude better. And I didn't get into that because everyone talks about how much better their system is than any other system. But at least in principle, these types of systems for a particular type of structure and application and whatever else are literally orders of magnitude better than a silicon type of circuit. And that's and we've actually published several papers on that before we even understood these issues here.
But being able to communicate long distances to other neurons?
Well, One thing I did not tell you is something that's in a paper that's currently being reviewed, and that is we have built an active transmission line. So we've successfully built essentially a wire that will conduct a signal, not an arbitrary distance, but a fairly good distance with, actually, it's not even a zero loss of signal. It actually has gain of more than 1. So we've been able to amplify a signal inside of a metal wire.
This is an action. Thanks. Ian.
Thanks, Stan. My question is, your model, you're showing diffusion or movement due to the concentration gradient or current direction, but also thermal diffusion. Did you consider in the model that in the thermal diffusion, depending on material and mobile species, the direction of diffusion may be opposite?
Well, I didn't show anything about diffusion at all in any of my, any of my equations. Now, the issue is that when you have a current channel form, you have a high temperature region within a material, and because of that high temperature region, you can create diffusion fields. In particular, you can create thermophoresis, and it's my contention that this thermophoresis is actually the mechanism by which forming occurs in a non-volatile memristor. So what happens is, people talk about forming or some sort of pre-breakdown or whatever. What happens is these systems have negative differential resistance. You get into a realm of negative differential resistance. You create this hot channel, and if you're in a material that happens to be fairly unstable at that particular temperature, then it will undergo a chemical change. There's also the possibility of species diffusing in the system. But that's the topic of yet another paper.
Michael Schick, Forschungszentrum Jülich. The asymmetry breaking you observed in the current, would you identify or regard this as a kind of a network effect in this system, what you also see in coupled oscillators, which suddenly break into different frequency regimes?
Well, clearly, a lot of the mathematics is similar. And I mean, it's an issue of a response to a instability in the system, and the system is trying to find an operating range which is optimal at some level. So from that standpoint, there's a lot of similarities, but given that both of these theories have coexisted simultaneously for 60 years. And to my knowledge, no one has ever even compared them against each other. That is like, that just varies on crazy. But the actual discontinuity, or the actual break in symmetry is not exactly coincident with the formation of the oscillations. They actually have two slightly different root causes, and they are actually separated from each other by a little bit on these devices.
Thank you for a nice talk. I'm John at Max Planck Institute, and I also work on vanadium dioxide and measure the current-driven transition and oscillations. So maybe follow up your previous answer. What's your opinion about the two theories which conflict for 60 years? Do you think they're both right, and do you find any contradictions between each other?
Well, as I said, both of those theories are essentially right, but the people who are responsible for the theories essentially said, well, my theory is got to be right because I'm so smart, And that means that this other theory has to be wrong because it doesn't agree with my theory. And so that's been the case for like 60 years. It's people not actually attempting to understand what the other person did and what the results were. It was just, well, I'm right and you're wrong, and that's the end of the story. Whereas, you know, we actually went in the lab and did the measurements. We collected the data, and we saw that both things occurred in the same material at the same time. So that's the reason why you go into the lab. You don't just rely on the theory.
Thank you.
Any other questions? We have just a little bit of time. If not, I might ask one for you, Stan. So in thinking of the larger neuromorphic community and a lot of the presentations you've seen, some people are using still leaky integrate and fire neuron models. Mm-hmm. Based on what you talked about today in your own thinking, what would you say to them?
Well, I mean, leaky integrate and fire is a proposed mechanism that actually can be built using these devices that I've just shown. You can do other things as well. I mean, once you understand that what you've got is an amplifier, you can start to think about building various types of circuits based on a different type of amplifier that amplifies based upon a DC bias in the system. So there's no third terminal, there's no gate, but can you create a system that looks like leaky integrate and fire using these devices? Well, absolutely. It's just an amplifier. So you just need to apply yourself appropriately.
Yeah, Stan, thanks for cutting out half the biographs, but give us time to discuss. But yeah, I think I understand everything roughly, and I think the controversy comes down to not taking into account the distributed nature of the device, right?
Yes.
Yes, the theorists are really treating it as like some atomic device or something.
Yes.
But it's extended in space and time, and there could be a different solution where the temperature is not uniform across the device and the flux is not, and so on and so forth. So that's really great, very interesting insight. But I'm not sure whether your claim that it minimizes entropy is a conjecture or you've actually shown it, right? When you said at the line,
what I would say is,
yeah.
From my standpoint, it's a conjecture.
Yeah, okay.
There's a whole group at Santa Fe Lab, at the Santa Fe Institute, who claim they've proven it definitively.
Yeah.
But I can't follow their arguments. So for me, it's a conjecture, but it's one that I honestly didn't really understand very well until I tried other things, minimizing, instead of entropy production, just minimize entropy, minimize enthalpy, try this, try that. And it turns out that none of those other things actually provide anything useful. So this whole issue of entropy production minimization goes all the way back to the 1950s, and essentially to Prigogine, the founder of non-equilibrium thermodynamics. And so what I would say is it's the foundational principle of that.
Yeah.
But I being a lowly experimentalist, I just use it as.
So can you go back to your previous slide, just one back? I'm trying to understand operationally what that means. So are you saying that in steady state, this equation, if you set, the t equal to 0, then that's a steady state solution. At that point, entropy production is minimum. Is that what you're saying?
Yes.
Okay, we can work on that.
That's the hope.
Yeah.
That's
Okay.
the hope.
Thanks.
Okay, let's thank Stan one last time.